outreach lecture. So if this is your first time here, you can't hear anything? Okay. Is this... Can you hear me now? Is this better? Is this better? Is this better? Test? 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 Okay, a little bit better. Just all the way. There you go. Okay, all right, so welcome to another Astro McGill Public Outreach Lecture. If this is your first time, so Astro McGill is the outreach arm of the McGill Space Institute in the McGill Department of Physics here. So we do outreach activities like our monthly outreach lectures, which are usually given by professors and postdocs in the department here. But a few other things that we do, so for example, every month, we also do what is called Astronomy on Tap, which is also an outreach talk, but it's slightly less formal, and it takes place in bars. We rotate English and French by month. So this month, it is English, and it's actually occurring next Tuesday at McLean's on Peel. And it's also, there's a couple of talks that are shorter. They're like 15, 20 minutes, and it's less formal. So if you're interested in that, check out our Facebook page. But today we have our regular public lecture. But before we get to that, so we have our regular raffle for a t-shirt. If you filled out one of our surveys, thank you, and I will pick a raffle ticket. I'll pick this one. All right. The number is 490-2025. 490-2025. Nobody? Going once? Going twice? Okay, I'm picking another one now. Okay, we'll get there. I think our record is I pulled 4 tickets once. All right, 490-2031. All right, we have a winner. All right, come on down. If you come on down and follow Bryce, he will get you a t-shirt at the table outside. Cool. All right. So moving on. So tonight, I'm honored to introduce our public outreach lecturer speaker, Dr. Cynthia Chiang. Cynthia got her PhD at Caltech, and then she worked on cosmic microwave background polarimetry measurements, and then she moved to Princeton and was a postdoc there. And then she spent a year at the South Pole working on like cosmology experiments there, and then she became a faculty member in South Africa. You were there for how many years? 5 years. But then she was lured away by McGill and moved to Montreal, and where she is a professor here at the McGill Space Institute. And you just started in the fall, right? So very recently. And tonight she will tell us about some of her work and travels to exotic locations doing cosmology experiments. So take it away, Cynthia. We'll figure this out.
Yeah, there's some background noise going on here. Okay, great. I'm going to try to not trip over myself during this talk, too. Okay. All right, I think we're all good. Okay, well, thank you for the introduction, and thank you all for coming out to hear me talk about my work. So I'm Cynthia, and I'm relatively new here. So the work I'm going to talk about tonight is work that I kickstarted in South Africa, but I'm going to end with a little bit of what lies ahead and what we're bringing to McGill here. So I'm going to talk about the search for cosmic dawn. And to start off this talk, let me first describe what I do for a living. So I'm a cosmologist. So what that means is that we are interested in the study of the history and the evolution and structure of the universe on its largest scales. So kind of the big picture. So the sorts of questions that we're interested in answering are things like, how and when did the universe begin? What is the fate of the universe? What is the universe made of? So kind of big scale questions like these. And these sorts of questions have been asked by humans for as long as we've existed. So to illustrate this, the picture in the slide that I have here is the Flammarion engraving from the 1800s. And you can see that even in those early times, the artist was thinking about what lies beyond and hoping to see something different if you look out into the sky. And so, the person who created this took a little bit of artistic license with the picture. So this is not quite what the universe looks like, but the spirit is still very similar to what we do in our scientific observations. So one of the wonderful things about cosmology is that thanks to the development of precision instrumentation, we can actually answer these questions in quantitative and scientific ways with specialized telescopes. So that's what I'm going to talk about today. So the beginning of modern cosmology as a science, rather than speculation, began with this guy here, Edwin Hubble. So he's shown in this photograph sitting at his telescope on Mount Wilson, observing galaxies. And this was around the 1920s or so. And Hubble discovered a really remarkable thing when he was looking through his telescope and at the galaxies. And the thing he discovered was this equation here. And I'm going to make you a promise that this is the only equation in the entire talk. So there will be no more mathematics after this. But I include this because it is such an important result in cosmology. And it's a very simple equation. So let me explain to you what this tells us. So what Hubble observed was that when he looked at galaxies that are far away, the speed, so first of all, the galaxies appear to be moving away from us, and the speed at which they're moving away from us appears to be in proportion to how far away they are. So in this equation, v is the speed, so the speed at which the velocity of the galaxies are moving away from us, and d is the distance that they are from us, and then h naught is this number that sets the proportionality between how far a galaxy is from us and how fast it's moving. And so the interpretation of this observation is that the universe is expanding. So the consequence of that observationally is that objects that are farther away appear to be moving away from us faster. And so with this very profound observation in the 20s, that began modern cosmology as we know it. So fast forward to now, if you guys want to be cosmologists, there are 3 things that I need to teach you. So I'm going to step through these one at a time, and I'm going to do 3 lessons. Okay. So the first thing is that as cosmologists, we would like to see into the past, because we would like to understand the history of the universe and where it came from. So the question is, how can we do this? And the answer is that our friend light, which we observe as astronomers and cosmologists, travels at a finite speed. So there is a consequence of this, which is that when we look at an object that's far away, it's taken some time for that light to come towards us. And so when we receive that light and we measure it with our eyes or our telescopes, we're actually seeing that object at some point in the past. So let me give you a concrete example here. Let's take the Earth and the Sun. So the distance between the Earth and the Sun is about 150 million kilometers. Now the travel speed of light is 300,000 kilometers per second. And so if you work out the math, it takes sunlight about 8 minutes to travel from the sun to us at the Earth. So what that means is that by the time we see sunlight, it's 8 minutes old. And so we are seeing the sun as it existed 8 minutes in the past. So another way of putting this is that if somebody were to pluck the sun out of the sky, or if the Death Star vaporized it and made it disappear, we wouldn't know for 8 minutes, and then we would know afterwards. So this is lesson number 1. First takeaway message is that looking at distant objects is the same as looking back in time. And that's the first piece of information that we need to do cosmology. Okay, so that's lesson number 1. I'm going to move on to lesson number 2. Lesson number 2 has to do with the kind of light that we're looking for in the universe. And it turns out that there's a special kind of light out there that comes from hydrogen atoms. And hydrogen is special because it is the most abundant element in the universe. So there's lots of it out there, and it's emitting this light. And so it's something that we want to observe. So what happens with a hydrogen atom is that it consists of a proton and electron. It's a very simple object. And the proton and electrons have spins associated with them. And so one way you can think about this is like a spinning top. And there's a pretty remarkable thing about hydrogen atoms is that once in a rare while, the electron spin flips upside down. And so an analogy for this is shown in this animated GIF here. If any of you have ever played with tippy tops, they're really wonderful little toys. They're these round-shaped spherical tops with a little stem on the top. And you can see that when the person starts spinning it here, it starts right side up, and then after a while it flips upside down. And so that's similar to what happens to an electron in a hydrogen atom, is that once in a while it flips upside down. And the remarkable thing that happens at that moment is that there's a flash of light that's emitted. And this light has a very specific color or wavelength, and it has a wavelength of 21 centimeters, or equivalently a frequency of 1.4 gigahertz. So this is lesson number 2, which is that the universe is full of hydrogen, and all of it is glowing with this light that has 21 centimeters of wavelength. Okay, let's move on to lesson number 3. Okay, this has to do with how light behaves when it's being emitted from objects that are moving. So there's a phenomenon known as redshifting, which happens when an object is emitting light and it's moving away from us. So this is what's shown in the top half of this figure, which is the sun-like object is emitting light, and the observer is seeing it on the right-hand side. And because this object is emitting light but moving away from the observer, what happens is that the wavelength of the light gets stretched out, or redshifted, as we call it. And the opposite effect happens when the object is moving towards the observer. So in that case, the wavelength gets compressed or blue shifted. And a similar thing happens, this same sort of redshifting and blue shifting that happens with light also happens with sound waves. When an object is moving towards you or away from you, the sound waves get compressed or stretched out. And so that has the effect of changing the pitch of the sound wave. So I have a little video to demonstrate this. Let's see, which one was it? Doppler. Right, yeah. Okay, so what's going to happen in this video is you'll see a car that's moving towards the person who's taking the video, and the car is going to be honking its horn at full blast. And as the car speeds towards the camera, you'll hear the pitch increase because the sound wave is getting compressed, so you get higher pitches. And then as the car speeds away, the sound wave is stretched out, and so you'll hear the pitch decrease. Okay, so I'm going to play the video now. Here we go. So you can hear the pitch increasing. And now the pitch decreases as the car moves away. Okay. So I'll play it one more time just so you can hear it. So that's the basic idea behind red shifting and blue shifting. So let me see if I can go back to my slides. Okay. So because the universe is expanding, distant objects, recall, are moving away from us. And so as those objects are moving away from us, the emitted light is red shifted, so its wavelength is stretched out. Okay, so that's all you need to know to do cosmology. That's lesson number 3. So now we are going to put all of these pieces of information together. Okay, so step 1 is, as cosmologists, we want to decide how far back in time, or equivalently in distance, we want to look. Right? There's a particular period of the universe's history that we want to study. So we choose that time and distance. And then the step 2 is that from Hubble's law, we know that at some certain distance, we can calculate how fast things are moving away from us at that particular distance or time. Okay? So then once we have that speed at which objects are moving, we know that most of that stuff is hydrogen, and it is shining with this light that has 21 centimeters of wavelength, but that wavelength has been stretched out because that hydrogen is moving away from us. And that the amount of redshifting or stretching of the wavelength is in proportion to how fast the hydrogen is moving, or equivalently how far away it is. So if we put this all together, the punchline take-home summary is that we can observe a specific time in the universe's history by literally tuning our radio to the correct wavelength. And so we can dial into a particular period that we want to study. So that's all you need to do radio cosmology. So now you're all experts. And so now that you have the tools, the next thing we have to do is decide what we want to look at. So this is a map of the observable universe as we understand it. So we think that the universe began its life 14 billion years ago in a massive explosion called the Big Bang. And then the limit of our observations that we can see directly is about 0.4 million years after the Big Bang. So that's the oldest light that we can see, the afterglow of the Big Bang, also known as the cosmic microwave background. And that's depicted by the outermost surface on this spherical picture. Now, between us and the oldest light that we can observe, there's a lot of interesting things that have happened in the universe. So the universe has been expanding and cooling ever since the Big Bang. And immediately after the Big Bang, after the formation of the microwave background, the universe was very dark and boring. And so there's this period known as the Dark Ages, aptly named, where the universe is just full of hydrogen and nothing else. So then eventually the first stars turn on in this period known as cosmic dawn. And then eventually galaxies form and clusters of galaxies and the structures that we're all familiar with today. And we're sitting here at the center of the picture as the observers, looking out and trying to make sense of this strange and wonderful picture. So there's lots of interesting things to measure in this picture, and there's a number of experiments trying to map out this entire volume. But for tonight, the story that I'm going to focus on is just on one slice of this history, and that is the period known as cosmic dawn, which is when the first stars ignited in the universe. So we think that this period occurred about 100 to 400 million years after the Big Bang. And that may sound like quite a large number, but to help you put that in perspective, imagine taking the entire 14 billion year existence of the universe and compressing it down into a human's lifetime. Then in that scenario, the period of cosmic dawn would be equivalent to a human's lifespan, or a human being about 2 years old or so. So another way of putting this is that when we are studying the period of cosmic dawn in the universe's history, we're trying to understand what she looked like when she was a toddler. And she looked very different back then, just like humans look very different when they're 2 years old. So this would be a really wonderful thing to study. Now, reminder of the cosmology lesson is that there's hydrogen, and so it is emitting it's emitting light that we were trying to observe, and we're setting the time period that we want to observe at 100 to 400 million years after the Big Bang, and so that tells us what frequencies we have to dial into in order to study this period, and those frequencies are typically 50 to 150 megahertz or so, give or take. Okay. So that's our mission, is we want to build an instrument that can do this. And so the next question is, how do you catch a radio wave? How do you measure these frequencies? So there's good and bad news for this. The good news is that you may have recognized the megahertz unit on the previous slide, because that is the same megahertz that appears in your car radio when you're selecting FM stations, right? So this is great, because everybody has an FM radio. All of you have detected cosmic dawn photons before, so that's awesome. This is really easy. So you may be wondering why you're sitting here and not collecting your Nobel Prizes. And the sad answer to that is that if you try this at home, you will only pick up your radio stations and you won't get any cosmology. And the reason for that is because the signal from these first stars is very, very faint. So to draw an analogy, the signal from the first stars is kind of like somebody whispering to one ear. And if you set up your antenna in the middle of Montreal, the noise from the radio stations is like somebody screaming into your other ear with a megaphone. And so if you have those two coming into your antenna simultaneously, your antenna is literally blinded by all of the radio stations, and you can't hear any of the signal from the first stars. So that's very sad. But we are experimentalists, and so we try to fix this, and we try to make it work, right? And so one way we try to make it work is there are radio quiet places where you can do these sorts of observations. So here is one big radio telescope at Green Bank. This is in the National Radio Quiet Zone. So we can start off by asking ourselves, is this quiet enough? And the answer is not really, unfortunately. So I promised earlier that I'd only have one equation in my talk, and this is another promise I'm going to make, is that this is the only type of plot that I'm going to show, but I'm going to use it a few times because it's pretty important. So I'm going to take just a couple of minutes to explain what this figure is showing. So on the horizontal axis is frequency in megahertz. So this is like if you take your car radio and you dial around in stations. That's kind of like moving left and right on the horizontal axis. And then on the vertical axis is the signal strength. So basically how loud you would hear something come in on your car radio. And so you can imagine as you turn your car radio dial from the left to the right, it's pretty quiet at first until 88 megahertz, and then boom, there's a radio station. And right next door, there's another radio station and another one. Actually, it's full of radio stations. So this is not good. Like, we cannot do cosmic dawn cosmology from here, sadly. But that's okay, because Green Bank is not a particularly remote site, and so you can do better. You can leave civilization behind. And so this is an example of one working cosmic dawn telescope. This is the EDGES experiment that's in Western Australia. And this picture really doesn't do any justice to just how remote this place is. So I encourage you to look up this site. It's the Murchison Observatory in Western Australia. And just look on Google Maps because it's really wonderful. There's nothing around. It's fabulous. So this is one example of an experiment. And so we can ask the question again of, is it quiet enough here? And the answer is yes, it's much quieter in Western Australia in the middle of nowhere. So you can see that there's a few lines that peek through, so a few radio stations that come through faintly. But by and large, this is very, very quiet and a great place to do these observations. I wanted to give a shout out to Raul Monsalve, who has just recently joined us at McGill. So he's one of the leading experts in these measurements, one of the main people on this experiment. And this picture is great. This shows you what life is really like doing these experiments. Raul's not trying to hide behind his ninja mask. This is because Western Australia is riddled with flies, so he needs to keep them off his face while he's working on the telescope. And plus there's an emu friend in the back, keeping him company and cheering him on. So this is what life as an experimentalist is like. Now, EDGES is really fantastic because this is breaking news. So last year, February 2018, we think that we saw the first signal from the first stars ever from the EDGES experiment. So this is really exciting. And I really do mean first time ever. So if this detection holds up, this is the very first time we've ever seen the universe in this period of its lifetime. And it's the opening of a brand new period of cosmology. So new things to measure and new things to understand and explore. So there's one caveat to that, which is that this measurement is exceedingly difficult to make. So you can see we have to go out into the middle of nowhere. And the other difficulty is that if you don't understand your instrument completely, it's very easy to trick yourself into thinking that you've seen something when maybe it's just some instrumental effect. So for example, all of you are probably familiar with audio recordings or stereo systems that produce their own buzzes and hisses when you turn them on. So similarly, antennas are quirky and sometimes they create their own buzzes and hisses, and if you're not careful, then those can mix up with the signal from the first stars, and that can be bad. So the EDGES team has done a really careful job, but they are emphasizing that, highlighted in red here from the New York Times article, that the observations need to be confirmed by other instruments because this is such a hard experiment to do. So there are a number of experiments trying to weigh in on this detection and to figure out if it's for real or not. So for the rest of this talk, I'm going to discuss one of the experiments that I'm involved in, which is trying to say something about whether or not this signal is real. So this experiment is called PRIZM, which stands for Probing Radio Intensity at High Z from Marion. And this is a picture of the experiment in operation. So you can see that there's 2 antennas associated with this experiment. They're pretty small, about the size of a coffee table. And the signals from these antennas are piped to these orange shipping containers in the background where we have our readout electronics and our data acquisition. So the first thing that you'll notice about this experiment, and with EDGES as well, is that these are fairly non-conventional antennas. So when you think of telescope, you probably don't think of something like this. And so this is another one of the wonderful things about cosmology, is that you can't go to a store and say, I would like to buy a Cosmic Dawn telescope, please. You have to build your own because these things don't really exist. And so all of these experiments are designed and built nearly entirely by students. And so I want to say a little bit about that process and how this is all done. So this is a picture of my lab back in South Africa before I moved here. And there were 1 faculty member and 3 students who are working late at night to try to get our instruments put together. So these are the antennas that are being tested. And my PhD student, Liju here, is the one who designed the antenna support for this. He had no experience with mechanical drawing or design, but he just taught himself. So he started off by building a little model with bendy straws and cardboard and figured out the best supports for this, and then taught himself AutoCAD, and then we made this happen in real life and built it. So this is all student done. And similarly with the readout electronics, this is another one of my students, Austin, and he is an electronics expert. So he also had never done any mechanical drawing, but bashed his head against it for a while and eventually came up with this enclosure and then put it all together. And it looks a little bit messy, but I promise you it all works great. So again, this is all done by students. And then, and this is all old pictures from back in South Africa. But right now we are in the process of upgrading the experiment and building new subsystems to install as part of that. So I have new pictures from just 2 days ago. So there are, what part of our upgrade plan is to include solar panels for some of our antennas. And these are a couple of undergrads, Simon and Taj, who are rock stars and who put this system together. I told them that a selfie would be fine for this presentation. So this is them in action, and this is the lab at McGill now. So hopefully we are going to send this hardware down in April. All right. So that's kind of a picture of what the experimental side is like. And so now I'm going to talk about where we have this experiment installed. So the home that we have chosen for this experiment is Marion Island. And remember that the name of this game is to try to get away from people as much as you can. So this island is in the middle of nowhere, as you can see. It is 2,000 kilometers away from anything else. It's about halfway between South Africa and Antarctica. And if you zoom in on the island, it's this little tiny rocky thing that's about 25 kilometers across. And on the northeast corner, there's a small base that's used for scientific research. So that's shown in the upper right. All right, so since most of you, have never been to this island before, and probably most of you don't do field work, I want to take you on a virtual tour of what it's like to participate in a deployment. And so this is going to be just a lot of pretty pictures of how we deployed our instrument in 2017 was the first time that we installed this experiment. In order to get to Marion, this is our ride. This is the SA Agulhas 2. It's an icebreaker that departs from Cape Town. And so we left on April 6th in 2017. And this was our deploying team. So 3 of my students, Team Awesome. So this is Redima, Heiko, and Liju. And it's just the 4 of us who went down for this experiment. And that's Heiko climbing the gangway up to the ship on the right-hand side. So later that night, or next day, we finally left the harbor, and this is us departing Cape Town. So you can see the harbor mouth there, so red for port, green for starboard. And then the little ship over there is the pilot ship that guides us out of the harbor, and then it says goodbye to us and then goes home while we tootle off to the open ocean. So the next day, you see nothing around except for blue. It's really wonderful. What's not so wonderful and what's not shown in this picture is that as you travel farther south, you get pummeled by 5-meter swells and you get body slammed against the wall, but that's all part of the fun. So then after a few days of being slammed against the wall and people getting seasick, you arrive at Marion a few days later, and this is the site that you see. So this is the base. The new base is on the right-hand side. The old base is on the left. The new one is affectionately known as the Butternut Hotel because of its yellowness. And one of the other wonderful things is when the ship pulls in, there's a welcoming party from the king penguins. So they're not used to this odd-shaped object in their water, and so they come around and swim and say hi to us. So that's really lovely. All right, and then as you probably saw in the previous picture, there's not really anywhere for the ship to moor on the island, near the island. So transport to the island is via helicopter. So these are Bell 412 EPs. They're really wonderful machines, wonderful pieces of engineering. So that's our ride, and then they fly us all over to the base, and this is a view from the air as we're flying over. And then this is us, arrived at the base on April 12th of 2017, and we're all pretty excited to be there. So one of the challenging things about Marion is that once you arrive on the base, there's only a 3-week access window in which we can do all of our stuff. So just keep that in mind as I flick through the rest of the slides. Okay, so let me tell you a little bit about life at the base, just for fun. In a nutshell, it is cold, wet, windy, and exhausting. So the average temperature it hovers around freezing the entire time. And in April, the average temperature is about 6 degrees centigrade or so. Not much warmer inside the building, I can tell you. The average wind speed is about 14 knots or so, give or take. But Marion is legendary for its wind, and the windstorms get up to 50 knots or so, sustained maximum wind speed, with gusts often reaching up to 80 or 90 knots. It is not fun being out in those conditions, I can tell you. It is also a very rainy part of the world, so there's about 200 millimeters of precipitation per month. And the population of the station is pretty small. So when the ship arrives for this takeover period, there's about 70 of us at the base. And then when the ship leaves, there are 22 lucky souls who get to stay behind for the winter period and who spend 13 months at the base. I'll come back to that later on. All right, so when we first arrived on the island, the first thing that we did was select a site to install our antennas. And one of the things that we had to do was figure out we wanted to be far enough from the base so that if somebody was playing with their radios or their computers, we wouldn't see interference from that. But we also want to be close enough so that you can access the site regularly. So this is a picture of our students, trying to check out with this antenna if you can see any emissions from the base. And eventually we chose a site, not at this particular location, but pretty close by. And this is the site that we chose. So the base is, again, on the northeast corner, and you can see that there's this big hill nearby. And so that helps us, that helps provide some level of shielding against any emission from the base. So what we're essentially doing is hoping to hide in the shadow of that hill. So the site that we chose is back here, in the shadow, and it's 4 kilometers away, so a 1-hour commute time one way. And what this picture doesn't encapsulate is just how great that 1 hour hike is. So these are some of the things, or some of the conditions that we have to face when we take our daily commute to work. So the first thing is mires. So because Marion is very rainy, it's covered with swamp, essentially. So there's layers of matted vegetation on top of water. And if you're not careful, sometimes you lose a foot when you go in. Sometimes your whole leg goes in. It just depends on how lucky or unlucky you are that day. So that's Redima in the background falling into her very first mire. And then the island is volcanic, and so there's also black lava rocks everywhere, so that's shown in this picture. And again, if you're not careful, they twist your ankles, or if you fall, you cut your hand. Again, not super fun, but we do it for the science. And then to walk around the island, we wear these really comfortable gum boots to hike around. So yeah, again, not great. And then, of course, the weather doesn't cooperate most of the time, so there are these 80-knot wind gusts and horizontal rain and ice pellets that sandblast your face. But it's okay, because the science makes it all worth it at the end, right? All right. So once we chose our site, the next thing that we had to do was final test at the base, and then this is a picture of my students just deciding whether or not it's okay to go, right? So this is kind of the last chance to do anything in the warmth of civilization, well, warmth, quote unquote. But this is, you have to make sure everything is in your shipping containers before you go, because if you don't have enough spares, then you're hosed. So it's pretty nerve-wracking before deciding to say, okay, thumbs up, time to go. But eventually, we decided it was time, and so we called up our flight crew friends to deliver our cargo. And for those of you who are here for the pre-talk entertainment, I was playing a video clip of them delivering our containers out there. So this is a view of inside the helicopter when this is the one time we got to fly, so we got a lift that one time. Every other time we had to walk. And so they delivered our cargo containers, and so there's 3 containers containing all of our antenna parts, and the base is 4 kilometers that way. So they dropped off our cargo, said goodbye, and left us. And then we started assembling the antennas. So this is the first antenna that we installed. This is the smaller of the 2. And I'll mention as a side note, Redima over here is actually a data analysis expert, so she spends most of her time programming. But in the field, it's equal opportunity hardware time for all. And so she is lovingly coating all the bolts with marine grease before putting them on the antenna assembly. And what's remarkable is that everything worked the next day. So we managed to assemble everything. All the pieces talked to each other, and we got first light from the experiment. So for those of you who don't do astronomy for a living, first light means the first time that you get light coming into your telescope, and then through all of the electronics chains, and then being read out on the computer. So this is a really important thing, because that means that all of the pieces are playing well together. Every individual piece works, and you can record data. So that's what these little colorful splotches are on the computer screen. And I know it's not much to write home about, but words cannot describe the feeling of relief when you see this coming through from your antenna. And I know the students look cold and miserable in this container, but I assure you they were just as ecstatic as I was to see that everything was working. So this is from the first antenna, and then we scrambled to get the second antenna up and running the next day, and remarkably that all worked the first time as well. So that was the good news. Then for the next week, we had just about a week and a half to make sure that everything was robust and ready to stay behind for the winter. So one of the other challenges of Marion is that the island is infested with mice. So that was one of the challenges that we spent the last week tackling, which is that mice really like to eat electronics. So they like insulation, heat shrink, electrical tape, anything that you leave out that's soft and squishy. So they did get into our electronics a few times. We had to figure out how to keep them out. So eventually, with some trial and error, we did manage, and we managed to mouse-proof our system. I don't know if you can see in this picture, but we have our little logo on the door that says no mice allowed there. So, all right, so that was the last bit. We had exactly 1 afternoon to take off because the schedule is so compressed and so busy, but we did take 1 afternoon off to relax, and we visited our penguin friends out by the beach. There are 4 kinds of penguins on Marion. It's a really wonderful place. Then the last day of summer operations was May 4th, and so this was our site before we closed up shop and went home. And then that was it, and we said goodbye to the island. So all of us said goodbye except for our overwinterers, and so I want to give them a very special shout out. So our first inaugural winterover was Kagiso Malepe, who took care of our system in 2017. And Vuli Manuka is down there right now as I speak. And these 2 guys are, they work for the South African National Space Agency, and they are superheroes. So Kagiso spent his 13 months, and Vuli has a few more months to go. We'll see him in April, and then we're going to bring bring him a lot of chocolate, and then he's going to go back home. And then the cycle will repeat again. All right, so the question is, was that all worth it? That was a lot of effort and a lot of pain. So how good is our new site? And the answer is, it is pretty awesome. So this is, again, one of these signal strength plots. And the red line shows the power that we see from Marion, and we don't see anything in there. So for comparison in the background, the black line that you see there is the same sort of data that's taken from a very remote desert in South Africa. So it's actually about as quiet as the Western Australia desert. Excuse me. But you can see that even in this premier radio quiet site, you still see a few radio lines coming through from FM stations in the black curve, whereas from Marion, there's just nothing visible. It is dead flat. So this is really exciting. This is possibly the most radio quiet site in the world that I know of anyway. And so this experiment, PRIZM, is operating right now, and analysis is ongoing. So stay tuned for updates. This is very young. We're only 2 years old now, but it's the beginning of something pretty exciting. Okay, and so the last thing I wanted to mention is that, in this quest for quiet places to do observations, there are other places that we're looking at as well. And it turns out that there's a lot of empty space in our backyard here in Canada. And McGill happens to operate an Arctic research station that is way up there. So that's pretty far from people as well, in addition to Marion. So wouldn't it be nice to just go into our backyard to see if we can do radio observations from there as well? So I'm really excited to share with you that I put in an application to do these sorts of observations, and it was approved just yesterday. So received the good news. Thank you. So July this year, my team and I will be heading up to Mars, the McGill Arctic Research Station, to do some site scouting, and hopefully we will find that it's quiet there, and if it is, then we're going to start taking over the north with our antennas. Right. So I'm going to end here and just end by saying that I hope I've convinced you that radio astronomy lets us explore uncharted territory in the universe's history. And there's a lot more observations that can be done that I haven't had time to talk about today. But one particular class of new experiments is searching for the birth of the first stars, also known as cosmic dawn. But the most important thing that I hope I've convinced you of is that this work is tremendously fun. So we get to think about really big science questions, we get to build instruments and play with toys in order to answer those questions, and we get to go on these sorts of wacky adventures. And they pay me to do this for a living. So for a job, I really couldn't ask for anything more. So I'll end there and take questions. Thank you. Thanks. Right, yeah. So, yeah, the question is kind of the nature of the Big Bang and how to reconcile that with the picture that I drew. So the answer is that you're right that, well, we don't really know what happened before the Big Bang and what the universe came from, but the Big Bang did appear everywhere in space at the same time. So it's not like the universe started from a point. The explosion was everywhere, and the universe was just created. The thing that I drew in my picture was what you can see as an observer looking out. What you can see is kind of a sphere around you. So if you were to look in all directions, then the diagram shows that if you look at a certain distance, that corresponds to a certain time, and so that is a spherical shell around you. And so then you can try to look as far back as what you would see from the afterglow of the Big Bang. And if you look that far out at a particular distance, that sets your radius. And so then if you look around in all directions, then you see that same glow. But it's focused on you as an observer, so that's kind of your sphere of vision around you. But that light exists everywhere in the universe. So that picture is just focused on the observer in particular. Yeah, excellent question. So the question was if you can combine the antennas to do what's called interferometry, which is where you take multiple antennas distributed at different locations, and you kind of combine their signals to form a super telescope that's much bigger than any individual hole. And the answer is that for the particular experiments that I showed today, those are not working in this interferometrically combined mode. So each one of those antennas is measuring total power. So it's essentially a fancy thermometer where you just set down your antenna and all the signals that you receive, like that's what you get and that's it. So you're just measuring how bright that signal is as a function of frequency, so as you tune your telescope. But actually the second answer to your question is that yes, actually, as part of an upgrade, we are planning on expanding our observing program to include new antennas that will be combined interferometrically. And the benefit of that is that you're now no longer measuring just a single number, so brightness as a function of temperature, but you can actually start to make pictures of the sky and see how that brightness varies across the sky. So this is all very early work, and we haven't done that yet, but that's the plan for the future. Right, the question was internet and remote access. That is another disadvantage of Marion and one of the challenges. So internet is only from the main base, and it's about the speed of a dial-up modem for those of you who are old enough to have worked with those. And usually it's only alive when it's not rainy, and this is one of the rainiest places on Earth. So, so if anyone tries to email me during April when I'm on the island and I don't respond, that's why. So yeah, unfortunately, the bandwidth from the island is too small to transfer all of our data back, and certainly from our site, there's no way to transfer it back over a cable. So we just have to write it to disk on site, and then somebody physically carries it back afterwards. Luckily, the data volume is very small because we're just writing spectral information once every few seconds. So it turns out that for those of you who are familiar with Raspberry Pis, there are these single board computers that you can get for about $30. And we use those in our backend to read out our data, and we just store the data to an SD card on there, and that's it. So small data problem instead of a big data problem. Great, excellent question. So that was about satellites and if they cause any interference for us. The primary satellite constellation that we can see is Orbcomm. So it's a communications satellite system, and that broadcasts at around 137 to 139 megahertz or so. But that's really the major thing that's in our frequency range. So I didn't show you the full range of our data, but the last plot that I showed where is dead flat with the red curve, if you were to extend it upwards a little bit, you would see the satellite signal come in. But that's okay because it's only it's a very narrow feature, and we know those frequencies are bad, so we just cut those out, and that's okay. And actually, it's sort of a security blanket because when you turn on your system and you see the satellites, you know everything is alive. So it's kind of a relief to have it there. Yeah. Yeah, so the question was what other research is done on Marion, and actually this is the first radio astronomy that's been done from there. So the closest research that has been done previously to our stuff is space weather research, so it's not really related, but at least they have antennas. Most of the other research is studying animals, so doing geology and biology research, a lot of people counting penguins and seals, and looking at the lava formations, things of that nature, plant studies. So. We are one of the very few people looking up instead of down and around. Right. Another excellent question is are there plans to put these out in space? And the answer is yes. Some people are thinking about this. Space has the benefit that yes, you can hide behind the moon to use that to shield yourself from the Earth, and you're also above the ionosphere, which is another kettle of fish I didn't get into. But yeah, the ionosphere causes problems for us. So there's a lot of benefits for going to space. The tricky thing is the price tag. So satellites are expensive and they take a long time to develop, but there are people thinking about this. So there is a proposed mission from the US called DAPPER. There's another Indian mission called Pratyush that's being proposed, and actually the Chinese have already launched something. So there's a couple of instruments that piggybacked off the Chang'e 4 launch, and so let's see if I get this right. There's the two Longjiang microsatellites that are in orbit right now, and then there's also the Netherlands-China Lunar Explorer that has achieved lunar orbit, and I think the instrument turned on a month ago. So these are exploratory experiments, and nobody knows what they'll see, but they're trying to do some low-frequency observations from space already. So we should hear something from them quite soon. It's all very new. Right, so the question was if we're recording a frequency that shifts around in order